So as you were saying, you're just trying to apply the rational root theorem. So using a rational root, let me just say RTT, using rational root theorem, x square minus 2 has no rational roots. I know it is a trivial fact otherwise also, but yeah, has no rational roots. Okay. So that implies that square root of 2 is not rational because it is one of the roots, right? That is fairly trivial, right? There's absolutely nothing in this. Okay. But then the homework, which is what I said I will be doing, because yeah, so we just give this homework, and this is equally trivial, but don't do it now, do it later. Show that 2 to the 1 by n is irrational, right? And why 2? You can say anything, right? Any integer m power 1, m not equal to 1. Is it true? No, it is not true. So yeah, it can be right, it can be rational. So yeah, 2 to the 1 over n is the simple way to say this question is 2 to the 1 over n is irrational. So this is one question. And the other question, which I cannot promise whether it will come from rational root theorem or not, but you could try to show this. I'm sure this is true, is irrational. Okay. Maybe you can also use a rational root theorem in that. Okay. So you can see what is happening, right? Rational root theorem is telling you what the rational, if something is rational, then what can it be? Okay, because all these numbers, whatever they are, they may be irrational, they may be rational, we don't know, we feel something but we don't know. But what we know is that there are polynomials which satisfy these numbers, right? For this is for all n greater than, strictly greater than 1, I suppose. Okay, so what I'm trying to say, you can prove it for, maybe you can prove the square root of 2 plus square root of 3 plus square root of 4 plus square root of 5. That much also you can try to do. Okay, you can do it for some small n also, I'm fine. But try it and try it. Okay. But what the philosophy here is that these numbers satisfy some polynomial equations. Okay, like you just saw the square root of 2. In fact, that's the definition of square root of 2, right? These numbers satisfy polynomial equations and rational root theorem. So they are roots of some polynomial equations. Using rational root theorems, you can say what the rational possibilities are. Okay, and then you will check that they are in fact not possibilities, and hence that polynomial you made will not have any rational roots, and this number will be a root of that, and so it will not be rational. This is a technique. This technique, I don't think it is easy to substitute with other techniques. So it's not a trick. It's not just a trick that you can take a time and do it in some other way. Maybe you cannot do it if you don't use this technique. Why? Because this is like the definition of this number. Otherwise, what does that number mean? Square root of 1. What does that 2 to the power 1 by n even mean? It doesn't mean anything otherwise, right? So that's the point. Okay, so that's why this technique is very, very useful. So this is one of the aspects of the rational root theorem. Okay, so Nagesh, do you have any questions in rational root theorem which you tried and could not do? Want to discuss anything?
I did about 3 to 4, but I think I
You were
got solutions for them.
okay. Then it is fine. Good. So then it's fine. So, but these aspects of rational root theorem, maybe if you have not done these questions, you should try these. Okay. So now I want to speak of maybe another aspect of rational root theorem, which is maybe is more interesting. In fact, in one of our master's exam class test, there was a question which was based on rational root theorem, and I could not do it. Okay. Of course, that was not this. That was rational root theorem, but it was not for integers and rationals, but it was for some other ring, which is objects which are like integers, but they're not integers. But they are complicated objects, but they are invented to actually study integers. But it was between those objects, and it was a kind of rational root theorem. And I knew the philosophy, but I couldn't get the answer. And the answer was a one-liner. Yeah. Anyways, so that was a yeah. But no, I'm not going to talk about that. Probably cannot. I have to prepare for that, I think. Yeah. But what I can say is something. Yeah. So in fact, I was asking that question, right? So how do I want to say? Just a minute. So see, like, uh, uh, what was the key to the rational root theorem? Right? So let us try to abstractify the rational root theorem. Not for complicating things, but for solving questions. In fact, we'll see. Abstractify the rational root theorem and see what we really needed. Okay. So if you see, so we had something like this, right? So we'll just do the monic version, okay? Because that other version is same in philosophy. There is nothing. So there is this polynomial. Okay? And then we said that if there is a rational root, then if there is a rational root, then it is an integer root. Okay. Yeah, that much we want to say, right? So if p by q is a root, so can I say this without talking so much? Yeah, maybe I cannot. It's equal to 0. In the end, what happened was that there was this one side. Hmm. So maybe this version we did not do, we did the other one, but it's the same thing. I asked you to check it. Yeah. What did we do in the end? Right? In the end, we had this kind of thing, right? And how did we get our like how did we conclude that Q has to be 1? Right? So we concluded that Q has to be 1 by saying that this Q divides the right hand side, and so it should divide the left hand side, but Q has no factors with P, and so Q has no factors with P to the power n. So Q has to divide 1, and so Q is 1. Okay, but try to understand what is going on. Let us say that Q is a prime. Okay, so you have a prime number in this. So you have something which is sort of an indecomposable. Okay, and then we said that so suppose Q is a prime. Okay, and then we said that okay, Q must divide the left hand side, but Q is co-prime to P, so again same thing, right? So at the root of it, we are using that. What are we using? That integers have a prime factorization and a unique prime factorization, right? A prime number either divides a number or it is co-prime to that. You see, right? So these are the things that every number P is not a prime. Sorry for the notation, but P is not a prime, right? P will have some prime factors, right? Now Q is a prime, so Q is co-prime to this, okay? But what we're just trying to say is that that just means that Q doesn't share any factors with any of these, right? And so Q has to divide the other thing. Why are we saying that? Because if Q divides, so Q, look at this, Q divides P to the power n, what does that mean? That means that Q is equal to, or rather Q times, right? Look at this very carefully. This fact we already know, but it means that Q times some m is equal to P, right? Or P to the power n. But if you look at the prime factorization of P to the power n, is this, but then we know that prime factorization is unique, right? We know that prime factorization is unique. And so, so Q must occur as one of these prime factors, right? That comes from prime factorization is unique. We never say it like that, right? So if we always say that if Q divides a number m, whatever Q divides a number x, then if Q is prime, then x has that thing as a prime factor. Everybody knows this. But why? It is because it comes down to the unique prime factorization that every number has. Do you people follow this? Right? This comes out of that,
Yeah,
right?
yeah.
It comes out of that thing that everything has a unique prime factorization. And so if so Q times m is equal to x, so prime factorization of x, Q is a prime factor on this side, so it must come on that side also. That's the thing. So basically you see, so anywhere, any place where we have unique factorization, this kind of theorem will be true. Okay, that is the moral of the story. So from here, I want to, okay, so any place where we have a unique prime factorization, this thing is going to be true. Now I'm going to just take things a little bit up, okay, and so you have to see if you can take this and tell me. We'll see, okay, we'll try this. Okay. So we know that Z has unique factorization. Ticked. Maybe you cannot prove it directly. Maybe you cannot prove it if I ask you right now, but it's fine. You know it's a fact. It's not a trivial thing to prove. It's not very hard, but it's okay. We know this. Okay. We know primes, we know what are primes, we know the definition of prime and everything. And so with that definition of prime, so what does this mean? It means that every integer is a product of primes with certain multiplicities in a unique way, which we understand. Okay, so for this, the notion of prime is important, otherwise you cannot even make the statement. And then the uniqueness also comes. Okay. Now today maybe I will want to say that, and this kind of technique can be used in many places, can be like a tool in number theory. This has unique factorization. Okay. But you should ask, well, what does it mean for something to be prime in this? What kind of elements are there? There is 2 plus 3i, right? There is 1 plus I, these kind of things. And even integers are there. I is there, right? So Gaussian integers is what these are called. Okay. But this also has unique factorization. Okay. And just a second, sorry. So yeah, okay. How will I tell you? How will I say that it has unique prime factor, unique factorization? Yeah. So anyways, let me try. So Zi has unique factorization. This is my claim. Okay, and here we will learn some tools. Okay, um, mm, 1 second. So if I want to say that Zi has unique factorization, first I have to tell you what are primes in Zi. What is the definition of primes? Right. What is the definition of primes and just things like that? Okay. So what is the definition of prime? That's number one. Okay. And through all this, we'll learn some good number theory. All these techniques are useful. So, uh, so that's the number one thing. But then, yeah, do I want to say that? So if I say that there is a Euclidean division in Zi, then I know that it will be a principal ideal domain. And then, yeah, sure, comes out of that. Okay, okay, cool. Okay, so so first I will have to I'll try to do this. So yeah, so Z has unique factorization. Now try to see why Z has unique factorization. Now you may know proofs of this, but I am claiming that this fact follows from Z has Euclidean division. Okay, so this fact. Now Z has Euclidean division. Do you people know this? Of course. I will show that this implies this and this. This is the root. This implies these two things. Okay. So what does it mean that Z has Euclidean division? It means that given any, you can just take it for natural, I mean anything, right? You know that given, in fact, given any integers m and n, right? There exists q and there exists r, where, okay, so if I want to state this like this, maybe I will say that this m is in Z, right? Yeah, you can take it. You can actually take both in Z. Yeah, it's fine. Sorry, just take both in Z. Yeah. So I'm just saying what Euclidean division is, right? That you can take both of these things in Z, and there is this quotient such that and there is a remainder such that the modulus of the remainder is less than n, and greater than equal to 0. No, 1 second. So R is, and it is less than mod n. Okay, just 1 second. Okay, so is this something that you know, right? That given any, so you know this for natural numbers, right? That given any natural number n and given any m which is less than that, you can find this where, okay, I mean if where m is equal to nq plus r, right? And the r is less than n. And if you want nm, if you allow n and m to be negative, then it has to be said like this, because r we still want to be positive and its magnitude to be less than. Okay, so this is what we have, and this allows you for unique factorization. I think let us try to Let us try to prove that. Okay, so let us try to see if we can prove that R has unique factorization. Sorry, Z has, because I want to show you how it comes, if it comes in this way. Yeah, Z has unique factorization. Okay, so suppose that Z does not have unique factorization. Okay, then let let's see. Yeah, let N be the smallest. So basically, I will just show that N has unique factorization. Okay, because that will also imply Z has unique factorization. Is this negative number, negative of that. Let N be the smallest natural number. Let N be the smallest natural number which does not have unique factorization. Okay, then you see, but then either if N is prime, then it's a contradiction, right? Then we are done. If N cannot be prime. But then if N is not a prime, then N is a product of two primes, right? And you see now what happens. Now N is a product of two primes. Sorry, N is a product of two numbers. But then you see these numbers are actually less than N because it's a proper product, right? I mean, both are factors. N is a product of these two. But then you know that these two numbers have, but then you know that these two numbers have unique factorization because they are smaller. They will have. So the N was the smallest number which doesn't have unique factorization. Okay. So then A and B have unique factorization. A and B have unique factorization. Yeah, but then there is nothing to do, right? It's a problem. 1 second. Yeah. I mean, at least we get that they have factorizations. Uniqueness will come in a different way, but yeah, if they are A and B can be broken up into primes, right? By because of the N was the smallest, the A and B have have factorizations at least, right? Into factorization means a product of primes, right? So A is equal to some product of primes can be broken up into primes. Okay, so then you don't need Euclidean division here. Of course you don't need. So why was I thinking? And also this B will also have this factorization. Some other K prime, some other alpha. You see, fine. And then the product of A and B is also a product of primes, right? So then, so we have proved, so kind of in a way we have proved that every natural number is a product of primes, right? But I have not been able to show you why you need so I've not been able to show you why you, like, how does this thing come into the picture, Euclidean division. Okay, so we have learned the one thing, but we have not learned why it comes in the picture. Okay, no issues. Our goal is the same. Our goal is to show that Zi has unique factorization. So every number in Zi can be broken up into primes in a unique way. So 1 minute, I mean, there are some complicated ways to do it, but there is also, I was thinking there should be a simple way to do it. Yeah, maybe that is the simple way which I'm thinking.
Z has unique factorization. That's like the fundamental theory of arithmetic, right?
Yes, Z has unique factorization is a fundamental theorem of arithmetic, but we want to now go beyond that and try to say that Zi also has unique factorization. Okay, and obviously you may also be knowing that this if you do this, which means polynomials over integers, right? They also have unique fact, but again that's not easy to prove. That's not at all. That's difficult to prove actually. This is actually it's much more difficult than what we can do at the moment. It's showing that Rx, meaning that polynomials can be unique, is probably easier. This is easier. Okay, so there are some issues here. This is I wanted to get to the root of it, but then it will take a long time. But it won't take very long, I suppose. Let's try. If we don't try, then but we want to learn this technique. So let me see. Okay. Yeah. First, let me define what is the definition of primes in what should be the definition of primes. Okay. So yeah, that's important, I think. Definition of primes. Okay. In Zi. And this definition that I will give you, that I will say, will work for everything. Zi, it will work for Z also. It will work for, okay. Because you see the definition of primes that we give for Z. So what is the definition of prime for Z? Anyone? Just in Z, what's the definition of primes? Just you can say, anyone?
So it's a factor should be itself and one.
Okay, yeah. So factors shouldn't be itself and one. No, because no, that's wrong definition because those are always factors of a number. So can you say something more precisely? I know you know the definition. All of us know the definition, but you have to say it precisely. So n is a natural number. N is a prime. When is n a prime? N is a prime. What's the definition? So
That it can't be written as a product of two smaller numbers. That
yes, maybe that's the kind of definition which we should look for, right? So n is prime, and so we can say that n is equal to AB implies that A or B implies that either A equal to plus minus 1 or B equal to plus minus 1. Maybe this is fine, right? Smaller, I don't want to use the word smaller because we don't want to use too much things to say. We don't want to use the order, the structure. So we can, but it boils down to the same thing that if you factorize it, if you write it as a product of two things, writing as a product of two things is a very basic thing. So that is fine. And then one of the factors will be plus minus 1. Will be something which is which can always be put as a factor. Okay. So this is the definition of primes. This is a definition of primes for integers. Okay, now the question is that let's see if we can take that definition of primes here. Okay, in ZI, what happens if you take that definition? So if you take that definition, then the question uh, is 2 a prime in ZI?
No, you can write it as a product of root 3 plus I and product of, into root 3 minus I. Sorry, root 3 plus I into root 3 minus
Root 3 plus 5 into, no, root
I.
3
Plus
is not
I
allowed.
plus.
But root 3 is not allowed. 1 plus I.
Oh, okay.
Yeah. No, root, that will be too much. Root 3, uh, don't know if that is will work or means, yeah, but this in this case certainly it's not allowed. So this, so Aparna, do you see that this 2 can be broken up like this, right? Okay, and you can see that these two things are actually, these two things are not plus minus 1. They are, and also they are not like invertible, right? You cannot always put them as factors for free, right? They don't have like, so 1 by 1 plus I, this thing is not in Zi, right? Because if you rationalize this and whatnot, then you won't get integer coordinates, right? You won't get a plus ib where a and b are integers. So this is no. The answer here is no. So it is fine. I mean, the primes here, primes there can change. That's not a problem. Okay. So we can take this definition of primes. Okay. So we have defined what primes are. Okay. Now what we want to, what we are claiming, and maybe we can just assume that for a moment and just move forward, right? And we will see what happens. Okay. Now we are claiming that every element of this can be written uniquely as a product of primes. Is this fact obvious? Not at all. But now we know what is a prime, and so we can at least make the statement. So is it fine so far? Aparna, is a statement and this new thing?
I'm actually a bit confused. Like, can you explain what is Z of I exactly?
Yes. Yeah. Z of I is simply a plus ib, where a and b are in integers. So I is the complex number, right?
Yes, that's right.
And a plus ib. So these are interesting because these are complex numbers which have integer coordinates. So you should have told me long back, but it's okay. Maybe I've not done anything. Yeah, so far. These are complex numbers with integer coordinates. Okay. So now you understand how we are defining primes,
Yes.
right? So it will turn out it's not a good definition, but it will work in this case. Okay. Our definition of primes was written as product of two numbers, and one of them has to be plus minus 1. Now, with that definition, if you want to give here, then you see that 2, which was a prime, is no more a prime. 2 becomes like this, 1 plus I times 1 minus I, right? And 1 plus I and 1 minus I are not like plus minus 1, right? They are not invertible. Like, so you understand, right? So because you cannot do 1 by this is not in Zi, right? Because what is this? This is 2, 1 minus I, right? So it is half minus half I. Does not work, right? So that is my point. Okay, it's not in Zi. Yeah, half is not a, we want integer coordinates. So so it means that we have written 2 as a product of two other complex numbers which are in Zi, and so we have broken 2 up, right? So 2 is not irreducible, it can be broken up. Okay, and that is our definition of prime. that something can be broken up, then we will say that it's a prime. It's not a prime. Okay. Okay. So that is fine. Yeah. Now I'm making this statement. Now we have know what a prime means, and so now I'm making this statement. Okay. Is so for fine? Right? Okay. So this statement is completely analogous to what we say for integers. Okay. I'm not saying, I'm not giving a proof of it so far, and maybe I'll not give. Okay. But this is, let's say we assume this statement. Okay. Now we want to, so far is it okay? Aparna, is it fine? Yes, just make sure that it's fine. Otherwise, yeah, okay. Then it's fine, then we'll move on. Okay. Now we have another property of primes, which we have, right? We say that, so in integers, so in Z, right? In Z, we say that if P divides AB, then P divides A or P divides B. We say this in Z, right? Yeah. Can we prove the same thing in ZI? In ZI also we want to prove the same thing. Okay, so let P, so P is equal to some M plus IN is a prime. Okay, we know what that means. Now we want to say that if P divide, now you can ask me what does dividing mean, and I will define. If P divides this, yeah, probably there are too many new definitions today. P divides this, probably this is more experimental, I think. P divides this, okay, just to see how you can take this, okay. P divides this just means that, means nothing, it just means that this is a product. That's what P is a product of this times something. That's what dividing means, right? It can be said in terms of multiplication purely. That's all I'm saying. Plus x plus iy something. Just what the meaning of division should be, I've just written it. Nothing special. Okay. Now from here I want to say, can I say that x plus iy divides one of the two? That is what I want to say. You see what I'm trying to do, right? I'm trying to use this. So there is this very special property of primes that we had in integers. And if you go back to the rational root theorem proof, I was highlighting that it was very important in the proof, right? If P divides one of them, it should divide the, if P divides product of two things, it should divide one of the things. If it doesn't divide one of them, it should divide the other. Right? So yeah, that's what, right? Those kind of things is this, because if you have this and then you know P doesn't divide A, then you know P will divide B. So for those kind of things, we need this thing. So let's see if we can prove this. So we'll try to prove this on the other side. Okay. This is going to be the main property of primes that we want to prove. Okay. So yeah, let's meet there and try to do this. Yeah, maybe I will not do classes like this from all the time. I think it's just testing. Let's see how it is. How